Good morning, good afternoon, good evening in 15 different time zones all over the world. This is the second day of the HiPEAC conference. In the meantime, we have more than 850 registered participants, and today it is the industry day. The exhibition is running at this moment, so I would encourage you to have a look at the exhibition. And while you're waiting in the queue to talk to a person in the booth, you can maybe already visit the poster gallery or maybe attend the job fair, which is also part of the industry day. This is a year when we also officially announced the HiPEAC vision. So the HiPEAC vision is a biannual document. This is the 8th time that we do this, and we will introduce the HiPEAC vision 2021 by means of a short video, which we will show now.
In the 30 years since the advent of the internet, computers have changed how we live our lives. Tomorrow's computing systems will build a continuum of computing that will stretch from tiny, interconnected devices that operate at the boundary between computers and the physical world to bigger and more complex systems distributed across the globe. Software actions will be executed wherever they are most efficient and might even move according to needs relating to energy consumption or latency. This flexibility will be needed because these complex systems, which interact directly with the physical world, need dynamic orchestration to meet human objectives, as well as security measures to ensure safety and privacy, while offering a diverse range of services. At the interface between humans and the cyber world, virtual entities will be like guardian angels, orchestrating services and protecting people and businesses from the complexity and dangers of cyberspace. Because they understand humans' natural ways of communicating, these virtual entities will allow everyone to access the full range of services of this new era. HiPEAC will propose to and help Europe to consolidate its talents to create this solution to unify and synergize technical solutions that already exist and take them to the next level for the benefit of humanity. Want to know more? Read the full vision roadmap on the HiPEAC website.
Okay, thank you. You can find also the link to the new document, which is a 200-page document at the homepage of the conference. I would like to thank the editorial board of the vision and especially its coordinator, Mr. Marc Duranton, for all the efforts he did in order to bring this to fruition. Next, I would like to introduce the next speaker. HiPEAC was created in 2004, and for the last 16 years was funded by the European Commission. Today we have our project officer, Mr. Sandro Delia, with us, and he will give us a preview of the digital decade for Europe. Sandro, the floor is yours.
Thank you very much, Koen. I hope you can hear me and see my screen. I want to give you a very short overview of what is happening at European level in terms of digital technology. If you consider the time we are living now, the next decade, what are the big trends that we can see? There is the pandemic, of course. Very dramatic, very evident as effects. But there is a climate crisis that we should not forget. And there are lots of global tensions in terms of trade tensions and even military tensions around the world, which all have a big impact on Europe. How is European Union answering to these problems? For the climate crisis, the answer is twin transition, which is at the core of European policy for the next years. And twin means digital and green, or green and digital. The order is not very important because the two things go together. It's been made very clear at the highest level from Ursula von der Leyen in the European Commission that the European Green Deal is the growth strategy for Europe, and that is the main way to, let's say, to transform our industry for the challenges of the future. The other aspect of the global tensions are addressed through the idea of strategic autonomy, which is also very important for us working in the digital area, because it means not having walls or reducing global trade, but is about making sure that Europe can defend the strategic interest and so be autonomous in all the technologies which are at the basis of our life and our society. And most of them are digital technologies. So it's something very important for us. In practical terms, where is the money to implement this policy? There are two big parts. One is the standard budget, European budget, which is, managed in chunks of 7 years. So now we are in the 21-27 budget. And in this budget, there are the two digital programs, Horizon Europe and Digital Europe. And the other one is the Recovery and Resilience Facility, often named Recovery Fund on the media. Which is basically a temporary recovery instrument to repair all the damage from the pandemic. So it is a big economic shock that is given through the member states of the European Union to help economy to work again. What this means in practice. Horizon Europe is a very big program. It's the follow-up of Horizon 2020 that most of you know. And there is a specific part on key digital technology in Horizon Europe that will be published very soon. What is interesting here is that we have two aspects. One is the research for digital technology, so making a better processor, making better software, and so on. And the other aspect is using digital technology for research related to other areas. For example, I work a lot in this area of twin transition, and most of the activity for the twin transition are enabled by digital technology, even when there is nothing really new in terms of digital research for digital technology, but digital technologies are needed, for example, to have better robots that can manage things in the industry and make the economy more sustainable. So this is a double aspect to be kept in mind. Digital Europe is completely different. It's a new program and is dedicated to capacity building. What does it mean? It means making sure that Europe has not only good technology in the laboratories, but that this technology, digital technology, is available to the companies, to the economy for improving our lives. And there will be a lot of investment, for example, in supercomputing, in artificial intelligence, in cybersecurity, in those which are the key technologies of our digital world. Recovery and Resilience Facility, or Recovery Fund, or Next Generation EU are different names for more or less the same object, is a huge, let's say, bag of money, which is very important from a political point of view, because European Union decided to put together their debt to finance this recovery. And it's very important for us working in digital, because at least 20% of the money spent from the Recovery and Resilience Facility has to be dedicated to investment and reforms in the digital area. So this is a clear, let's say, measure of how much European Union consider digital technology important. So this is all from my side. And the message that I want to give is very short. First of all, Europe will invest heavily in digital technologies in the coming years. Second aspect is that the focus will not be only on developing excellent technologies. We are quite good in that, but the focus will also be on developing on one side and on deploying and building the capacity on the other side to make sure that this technology is really used. Third one is that the Green Deal is not only green, is also digital. Green and digital transitions are two complementary aspects of the same thing, that is the vision for European economy and industry in the future of a sustainable economy. That's all from my side. I give back the word to Koen.
Thank you very much for this very good news, Sandro. I think the future is bright for computing. And I would also like to thank you for the continued support by the Commission to our community, the HiPEAC community, for all these years. Thank you very much. I give the word to Diana, who is the chair for the keynotes. Diana.
Thank you, Koen. Good afternoon, good morning, and good evening, everyone. Welcome to our second keynote speech at HiPEAC this year. As usual with all of our virtual keynotes, the questions should be posed in the Q&A panel. Our keynote today is on the path to exascale and beyond, and our speaker, Dr. Brad McCredie. He's the Vice President, Data Center GPU and Accelerated Processing at AMD. He runs the data center GPU and accelerated processing business, driving AMD's data center strategy, covering data center GPU, CPU, and GPU solutions. Before joining AMD, Brad was an IBM Fellow and Vice President of IBM Power Systems Development. At IBM, Brad was responsible for system hardware, software solutions, and ecosystem development teams, driving advanced technologies to support customer needs. Also at IBM, Brad worked on the development of IBM Power 2, Power 9 processor families, and he also helped lead the creation of the Open Power Foundation, which is an independent group of global technologists who encourage the adoption of open server architectures for computer data centers. Brad holds all his degrees in electrical and computer engineering from the University of Illinois at Urbana-Champaign. And with this, I would like to give the floor to Brad.
Well, thank you, Diane. Appreciate it. And can you hear me okay, Diane? Yeah, she's
yes,
already on
we can
mute.
hear you.
Yes,
okay, good. All right, so we'll get going. So let me add my good morning, good afternoon, good evening to everybody. Thank you for attending this talk. I'm going to discuss, the path to an exascale. And as you heard, my name is Brad McCredie, and I lead the data center GPU business at AMD. I'm presenting you today from a rainy Austin, Texas. That's where I'm located at, and I hope my words are finding everybody in a safe and comfortable spot as well. I'm looking forward to next year, hopefully, where we'll all be back face to face again and get to greet each other personally and share ideas more freely. Today, I'm going to share with you a topic that I get asked about a fair amount lately, as we've announced our partnership with HP to deliver several exascale machines to Oak Ridge and Lawrence Livermore, as well as Lumi in Europe. And that question, of course, is what is the path to an exascale? How are we going to get there? I like to tell the story a little bit by looking backwards, looking forwards. We'll have a little fun, maybe compared to some other industries. We'll take a look at that and see what challenges we've overcome and what ones lie ahead of us and how we can tackle them. If we go to the next page, please. Well, we got the cautionary statement. As I mentioned, I'll be looking forward, and things in the future are bound to change. So looking at exascale here, one of the most exciting things for me and one of my favorite things to do is to build supercomputers. I think it's very rewarding. It's one of the most rewarding disciplines in our industry, and it's one of the most challenging. Leading in supercomputing is really leading in cost performance. If you want to win the HPC race, you got to win in efficiency. And it's very difficult to overpower and trick your way to leadership because the scale of supercomputing is just tremendous. And the consequences of placing a bad bet are very, very expensive. So in supercomputing, even more so than most any discipline, you have to do your homework. You have to place your bets on solid designs and top technologies. As a consequence of that, high performance computing, HPC, supercomputing has been and remains the bellwether of our industry. It's a tough master that quickly rejects bad ideas and quickly rewards great innovations. And it separates the wheat from the chaff. So many of the most enduring and impactful trends of our industry were tested and certified in high performance computing. And some of the easy ones to point to: parallel and vector computing, scale out processing with commodity CPUs, accelerated computing, with GPUs, just to name a few of the large ones. You know, the picture I have up here right now is a little example of the big impact accelerated computing with GPUs has had. You know, the left side is if you try and build a large supercomputer out of CPUs. The right side is if you go CPU and a GPU, and you can see the you know, advancements on the key cost, performance, power metrics. It's tremendous, the impact of accelerated computing. You know, each cost performance enhancement is generally driven by the need to overcome some technical challenge that was blocking the way. And so what I'm going to do is I'm going to take a little look at some of those first that we've overcome in the past. The next page shows a chart here, and I'm going to build on this. The y-axis here is cost performance. X-axis is time. I plotted on there Moore's law. That's the takedown curve of cost performance we want to stay on. I know Moore's law is a count of transistors on a wafer, but you know, its impact on our industry is that it's really the metric that we've lived by to drive cost performance. You know, if you look here, you know, this particular plot of cost performance is wanting to stay on the Moore's law curve. This was the first one when I first started building computers back in the 90s. This is how we measured performance was megahertz, and the cost performance metric that mattered was dollars per megahertz, right? If you had a, you know, way back then, if you had a 500 megahertz processor, I'd give you $100 for it. And if you showed up with a 600 megahertz processor, well, that was worth $150. And, you know, we were really driving things on frequency then. You know, I was thinking, you know, I dug out some of the old charts. We had some competitive analysis charts that actually showed that we thought, of course, that megahertz were going to just grow tremendously. You know, and these were the charts that we were using to predict the future. So back in the early 2000s, you know, we actually had the charts thinking we were going to get to 10, 20 gigahertz, excuse me, get to 10, 20 gigahertz with processors. And of course, that never materialized because, you know, we started running out of gas, oxides got leaky, power started overwhelming things. And so what do? We had a change. And if we go forward a page and we can look at what happened when we made the changes, we had to really start measuring performance because that's what mattered, right? So it was a good change. We went, instead of from dollar per megahertz, we went to dollar per thread performance. And this is went into the era of the architectural explosion. You know, we started going in order, out order, wide issue. You know, big focus on cache subsystems. You know, back here when I was designing processors back in this era, you know, one of the favorite catchphrases is the memory stupid. We started doing all kinds of things to get memory closer to the processor, reduce latency, tie the processors closer together. You know, dollar per second was definitely a core metric that we drove on here. But, you know, even these metrics ran out of gas. As you can see, we weren't able to stay on the targeted cost performance takedown curve. And we advanced a little more. So then we got to, you know, go to the next page here. We went on to and got to where we're at today, which is measuring dollar per throughput. Now, you know, this is what we do now. We're looking at rate numbers, and of course, you know, this is most obviously and well documented. We're in the multi-core era. We you know, started driving on scaling out, even at the chip level, and of course, we threaded our processors, and this is what we've been driving on, and we've done a pretty good job taking down cost performance here. But if you really think about it, right, you know, we still got a gap, and that's what the picture shows. If you go forward a page, we still have a gap that we're not able to strike our cost performance takedown that we've always wanted to go after. So what we do is we start finding ways to fill it in. And my partner is moving me right along here. So here we go. That's all right, Clarice. Let's go ahead. We'll go forward. You know, that leads me right into airplanes. And this is an interesting chart. I like to do the comparison because I was wandering and flipping through some material one day, and you look at this curve, and it was like the speed of airplanes stayed right on what we were on for the longest time with the frequency of microprocessors. You know, each Each generation was faster. We were on an exponential. This is a log plot. So this is an exponential growth curve, just like the exponential growth of microprocessors. You know, the first plane comes out, you know, it was going at a fast walk. You know, finally the Ford tri-motor, it's labeled there, it breaks 100 miles per hour, it gets from London to Paris in an hour maybe. And, you know, and I'm sure that was big news, and we had celebrated it. And then we go faster, 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 we get up there, and then we get to the top, and, you know, the Concorde, you know, it blasted out through the speed of sound. And then what happens after that? And that's an interesting picture. You go to the next page. Every airplane after that was the same speed. You know, the Concorde, actually the Concorde was, if you read about it, it was a commercial success. But the problem was it had a really hard, its problem was it had a hard time speeding up travel. While the airplane kept going faster, traffic on the way to the airport, the rate of baggage conveyor belts, they all were about the same. And so much of the performance, the time to get from point A to point B stayed constant that, you know, it really wasn't viable to keep pressing on to the faster speeds, et cetera. And so every other airplane is the same. And of course, that was the end of commercial aviation, right? Well, no. What did commercial aviation have to do? Well, it had to go and innovate in different directions. It had to find different ways to fill the gap. And that's what happened. You know, it's kind of funny. When I used to tell this story, then I'd go ahead and talk about the 787, which isn't pictured on this. And I would always point out that the 787 was sold out for the foreseeable future. I don't know if that's still true with the pandemic anymore. I haven't talked to the people at Boeing for a while. I used to visit there. They were a client, and they would always talk about being sold out. And what was the reason that 787 was sold out? Was it because it was faster than all the other planes and started going faster? No, that wasn't it. They innovated on a different axis, and they innovated along cost performance. It is the most efficient airplane out there. And that's why it was, you know, sold out for so long. I hope it still is, but I don't really know with the downturn in airline travel. But the argument I would make is that every industry goes through these exponential growth curves, and then they eventually peter out and go to having to innovate along the other axis. In another industry, we go to the next page, and this is another favorite example of mine, is the car industry. This is another one, exponential growth curve, decaying exponential. This is the speed. You know, this one I actually plotted quarter mile times of all the various cars out there. You know, we went through an exponential growth phase, and now we're starting to hit an asymptote on cars. This is I highlighted the Dodge Challenger. That actually happens to be my vehicle of choice. If you go to the next page, it really dawned on me when I was picking out. My son turned 16, and had to pick a new car for him. Well, not for him, for me. I gave him my old pickup truck. He got my old pickup truck. I had to get a new car for me. And I was looking at the Dodge Challenger, and I really got enamored with the vintage cars on the left, 1970 Dodge Challenger. Then Dodge, of course, was building a very similar looking car, you know, new trend, you know, with the retro styling. And so I started comparing them, and it was really interesting. If you can see, the two cars had almost identical performance specs. They're built 70 years apart. Actually, the two of them cost about the same too. Built 70 years apart and almost identical performance specs. And I was like, wow, you know, that they've really hit an asymptote in the auto industry. But if you know, so I started picking out which one I was going to buy. So you go forward a page, and you can look at the automotive industry. Same thing, right? You know, you got the car on the left, the 1970 Dodge Challenger, you know, 425 horsepower, and you got lap belts, and that's it. You know, so what did the automotive industry do? It did tons of innovation along safety. You know, now over on the right, you got your anti-lock brakes, you got your shoulder harness, you got your airbags, you got all kinds of stuff adding safety. You know, and you also got, of course, all of your electronics. You know, I never, well, don't get in the car very much these days, but back when I used to drive a ton every day, of course, you know, we had all the electronics to make it much easier to do your Bluetooth phone and things like that. I actually showed these charts when I was kicking off some of the microprocessor designs each generation. One of the last ones I kicked off when I was back at IBM, and everybody latched on to, and I kept telling them, I said, we need to go and find now the lighted cup holders of microprocessor design. Lighted cup holders is a great feature. When you're driving along at night, you don't want to spill your drink as you're moving along, but it's a small feature, but it actually kind of interesting, kind of fun. So that's every industry, if you think about it, goes through these exponential growth phase. We're doing the same thing. We'll move back to computers here. We're doing the same thing in the computer industry, just like they are in these other industries, and that's what we got here. And of course, the big asymptote to driving the discontinuity is the technology is not delivering, automatically for us like it was for so long. I used to always joke that, back in the days when we were in the golden technology scaling eras, it was easy to be a designer. You wake up in the morning and you already got a 2x every 18 months. Just send your design into the next technology node, got twice as fast, life was good. Now, we have to drive tons of innovations. And when you see these little red arrows, they represent, the innovations we need. And one of the things that really is sobering is that, technology was so great year in, year out, you would get the advancement of technology. But now, once you drive an innovation, most of them, we have to come up with a new one. Take one of the easy ones, accelerated computing, including accelerators and great 10x performance. But once you go ahead and put the accelerated, the GPU in there and get that 10x performance, you got your 10x performance again. You're not going to get 10x again. You got to go and find the next acceleration, whether it's network or something in software or some other cost performance advantage. You got to keep coming up with different ones each year. It requires a lot more innovation to move forward than what we've done in the past. So that's sets up. We know what I'm going to talk about here now is I'm going to spend the rest of this talk talking about a few of the red arrows on this page that we think are going to carry us forward into an exascale, and do that in an era where, advantage 1, 2, and 3 isn't, the one that's carried us thus far, which is technology scaling. So let's take a little walk through that now. Here's the first one, and you have to start here no matter what. In all cases, you have to start with the performance per watt. This is the key one. And what I showed here is this is a little bit of an AMD perspective on it. As AMD has gone and made a tremendous advancements and surgence in the marketplace, it is one of the key things that we've done is we've taken each one of our disciplines and made tremendous cost power performance improvement, which is very directly proportional to cost performance improvement in all of our various product lines and disciplines: desktop, server, graphics. And what I'm putting on here on the end, of course, on the far right is I have the data center GPU that will be driving our exascale computers. We are bringing all of those advances in technologies from those other disciplines into the data center GPU. And just like those have achieved leadership power performance, we will be achieving a leadership power performance with our designs. And that's certainly the backbone to finding your way to an exascale is definitely power performance efficiency. If we go forward a page, one of the key things to drive that efficiency is architecture. And one of the things that's happening right now with the general, we always talk about the GPU for computation, the general purpose GPU. One of the challenges it's facing right now is the general purpose GPU is becoming very general purpose. While we've, of course, have visualization workloads and computational workloads, the breadth of the computational workloads is growing tremendously now, as the AI features and functions and requirements are growing. Now we're getting into many different precisions and mixed precision architectures to cover the AI stuff. And of course, we still have our high precision needed for high performance computing that we're talking about a lot here. And then, of course, you know, innovations for gaming and visualization are coming at a tremendous pace as well. So if you go forward a page, one of the things that we're doing is they're saying, hey, you know, as we can go back and narrow or focus our designs on more narrow architectures, we can get to higher levels of efficiency, cost performance with two designs. And that's something that we have done. If you go forward a page, we have formally done that with our GPU architectures at AMD. We have our gaming optimized GPU architecture that we call it our code name, our Navi family or Radeon family. And then we have our CDNA architecture, which is our compute family. And we separated those. Are two completely different chip designs now, two completely different design points, each optimized for the architecture. And that's a really cornerstone and key piece for us to be able to go approach and attack, optimize the various workloads. So that's something that's driven as well as our cost power performance improvements just through design and innovation. We're also driving after power performance efficiency improvements with our architectures. Here on this next page, try to take a little bit of a crack at showing what that separating into a CDNA architecture can do. And these are a few of the parameters. So this is comparing our first CDNA architecture. It's labeled here called MI100. This is our first CDNA architecture GPU. And this is comparing it to its previous generation, which is our GCN architecture, which was both compute and graphics. And you can see we got a much higher density of compute elements, twice, 2x the compute elements on the GPU, which doubled our peak flops. And then one of the most important things is we were able to embed now what we call matrix core technology. But what this really is this is the matrix operations that are so prevalent in the AI workloads. And we were able to do about a 7x performance improvement on the low precision, mixed precision math compared to the prior generation with the resources we were able to free up, focusing on the CDNA architecture. Now you go over to you know, networking and or I should say, you know, GPU to GPU communication or I/O. We got a 4x performance improvement there. We were able to move to our next generation Infinity architecture. I'll talk about that in a second. And we were able to stay with HBM2 as our previous generation was. We got a 20% performance improvement in bandwidth talking to our HBM2 with this later generation. And most of that's enabled by focusing on just the compute elements versus, you know, focusing on both the visualization and the compute. All right, so looking at our next innovation, packaging has, of course, been a very key point of leadership for AMD over the years. We were the first to introduce the HBM into the GPU in 2015. We did that with 2.5D packaging, put the silicon interposers down, use that to connect between the processor and the HBM. And then, of course, we started leveraging multi-chip module packaging with our CPU designs, and that, you know, evolved all the way in 2019 to the chiplet architecture, all of which have just done, you know, everything that's on this page has been, you know, driven some very nice cost performance improvements and leadership in the industry. Looking forward, you know, it's very important, you know, over here looking forward on the right, you know, now we'll start getting into full 3D. You know, of course, our HBM has been 3D stacked for some number of years now, but we'll be applying that technology in the future to our processor designs as well. And that's going to, you know, first of all, you know, as we labeled on the chart, you know, enable a tremendous bandwidth improvement, you know, a 10x bandwidth improvement in the you know, communication between the chiplets. But also it's going to enable us to, you know, put much more silicon on the package. Now, of course, power limitations are going to force us to be turning that silicon on and off very rapidly, which we are getting very good at doing. But it's also going to drive a ton of performance, enable us to put a lot of computational elements in a very dense spot and drive good performance with that. So I think packaging is going to be a big big advantage as we start looking at where we're heading in the future. And then the corollary to that on the next page is of course, now connectivity and the architecture roadmap. So this is our Infinity Fabric. I like this chart because when I look at this chart a little bit, I can see the parallels between, the CPU evolution of connectivity between CPUs and what we have in the GPUs. So on the left, we got, non-coherent point-to-point buses between a CPU and a GPU. You could almost think of that as a front-side bus, what we were on so long for CPUs. Here we do have our CPUs as we've drawn and connected with our Infinity Fabric for coherency between the CPUs, but the GPUs are just PCI attached. Next generation, which is what we're doing now. Now we have the Infinity architecture between the GPUs, coherently attaching all the GPUs, likewise coherently attaching the CPUs. And then, we're showing the endpoint on the right, where we now have the Infinity architecture everywhere, as well as the very tight connectivity between the GPUs. So just like all CPUs are fully connected, the GPUs are fully connected. And what we're showing here, which is what we'll be doing with our next generation GPUs that we'll be using to deliver the Exascale processors, we have the coherency, hardware coherency between the CPUs and the GPUs. And that's a nice innovation, is well documented, that it does a great job of ease of programming, a lot less work for the programmers to keep track of coherency between CPUs and GPUs, as well as it's a performance advantage. When you have the hardware moving the data between the two memory subsystems. So the packaging that I showed on the previous page is one of the course key elements, freeing up the I/O and enabling the connectivity between the GPUs that's so important to driving performance at scale. Okay, looking forward here, software. I wouldn't want to be accused of being a hardware bigot, so we have software here, and then once again, you just look at the chart, you can see the rate of performance improvements that software is delivering. You can tell right away that that software is going to be so important to getting to an exascale. They can move the needle so much. Here we show now granted, this is when we were going through a period of very fast learning as we were developing and deploying our software stacks on the AMD computational GPUs. But nonetheless, you can see tremendous rates of improvement, 8x over the past 2 years for the software innovation on the GPU side. And in getting into the exascale, we can leave no stone unturned on the software pieces as well. And we're making large investments into both the compilers and the runtimes to get those performance improvements. This is the example that we showed with the ROCm 4.0. I mentioned the MI100 that we recently announced. The ROCm 4.0 is what we call our software stack that went with the MI100, where we optimize performance for that. Okay, looking forward a little more. So now we're going to look a little further out towards the horizon. This is a look backwards, but I thought it was a good way to introduce the topic. We've had a long history at AMD of building APU designs where we put both the CPU and the GPU on a single piece of silicon and obtain the efficiencies there. Of course, these are largely mobile computer targeted designs, and that's where we got most of our experience. And why do we put APUs into mobile devices? Because they're highly efficient. That also applies as well to the data center, and all of the learnings that we have here with the mobile devices with the APU designs, that will translate to the data center. So as we're driving for efficiency to get to bigger and bigger scale, get to an exascale, because like I said, the key to moving forward is efficiency. I think you'll see this learning and these type of devices at the data center scale, being very important and be a direction that we're going to be heading into. So this is, taking learning from our mobile devices and moving into the data center to get to the efficiency to go to scale. Go forward to the next page. I think this is my last chart. So this right here, right? You know, the picture on the left, that's what we have today. We got our processors going to be coherently attached tightly and working very closely with our GPUs. But as you go and look forward, right, there's still a lot more pieces that we can bring in, you know, more of those little red arrows to drive those efficiencies, to drive those capabilities for more and more workloads to accelerate. And so you'll see system level accelerations a lot. You know, we can bring in more devices. We got on, you know, some examples on here of FPGAs and examples of more workload targeted, AI targeted accelerators. A lot of work going on in those spaces in the industry right now. And I think we'll see that into our designs as we go to an exascale and beyond. And then as always, right, even to this point in time, you know, half the cost or more sometimes of these systems is memory, and we burn a lot of power there as well. So lots of innovation in the memory subsystem are coming. I think, you know, seeing new technologies being brought in to really drive down the dollar per bit and the power per bit is going to be very, very important, as well as architectures. You see the little note there that has a little discussion on fabric attached architectures. And I think those architectures will also drive efficiencies, both cost and power performance efficiencies as well. That'll be very important in moving us forward to an exascale and beyond. So with that, excuse me, I think I'm doing a pretty good job staying on time here. With that, we have a few examples of how we're going to be moving forward to an exascale and beyond. And I'm going to throw the floor open, or I see there's a few questions there. Throw the floor open to some questions, and we'll go from there. I think Diana, you were going to.
Yes.
Yeah.
Thank you so much, Brad. Yes, we have a few questions in the Q&A. And by the way, please continue to ask questions in the Q&A panel. Let me start with a question that is related to our keynote from yesterday, which was on in-memory computing. So one of the questions has to do with how important do you see in-memory computing to get even more efficiency?
Yeah, I think that's a good one. And, I tipped my hand on it a little bit in the talk. And what do I mean? I mentioned the APU, and I mentioned the fabrics moving all of those elements closer together. So the trend and the direction is there, right? As you get to tighter and tighter connectivity between the GPUs, what are you doing? You're really, with that coherency between the GPUs, you're really getting all the memory that's on those GPUs closer together so they can communicate better. Big efficiency improvement. We've seen big performance improvements. I discussed APUs. What are we doing? We're bringing the CPU memory in there closer to GPU memory. They're actually sharing the memory. What are you doing? You're getting performance and efficiency advances by really pulling memories closer together. What's next? Well, we're gonna, we'll take the computational elements, put them on the memory die. I think that trend's real. I think those efficiencies are real, and I think that's going to be an important piece as we move forward. So yeah, I think my short answer is, do I think it's important? Yes, absolutely. I think the trends are something that we're already exploring.
One question related to the types of applications that you see important in the future. So in general, some of these are suitable for GPU platforms. In other cases, they could also be run on FPGA platforms. Do you see any distinction between which of these would be suitable for GPUs versus FPGAs in general?
There's a lot of discussions. I put into my talk that I think we're going to see more special purpose, or getting to the purpose of the accelerator more aligned to the workload. If you take the generalization of the little pictures that I showed of the the general purpose GPU, or even just taking that and specializing into a visualization targeted GPU and a compute targeted GPU. And we're going to get better efficiency, better cost performance by making that break. You know, and as I wrapped the talk up and I said, hey, you know, in the future, we're going to get more targeted accelerators. I think that trend again is very, very real. We're going to see, you know, the accelerators become more and more targeted because you need that efficiency. You know, really, as the technology's not scaling, as the big hammer is not coming and improving cost performance for free, what do we got to do? We got to make our designs more efficient. Well, of course, we can make our designs more efficient by being more clever, building better designs. But at some point, we also have to make our designs more efficient by targeting narrower and narrower workloads. And that's how you improve power performance. So which exact workload is going to go to which device? I think the device is going to go to the workload. I think as workloads, you know, I mean, obviously you can see the trend in the industry right now that the AI workloads are very, very important. Big investments going there. What are we seeing? We're seeing a lot of devices targeting those workloads being built in the industry. A lot of the venture capital and that money is going there. So I think, you know, it's not going to be, you know, the way the question was phrased is which workloads FPGA preferable to. It's going to be which workloads will we be targeting the FPGA to, because the FPGA can be targeted to many things, and it'll be the workloads that are most important to us. I think we need to think that way a little bit more.
Next question. What is the position of AMD related to RISC-V?
I don't think that's really relevant to this particular presentation. I'm gonna pass on that one. Is we don't really have a position relative to RISC-V right now.
A couple of questions. The first one has to do on programmability. What are the efforts that AMD is pursuing on easing programmability?
Yeah, I think that's one of the most important ones. I was looking at that question. I think that's a really important topic on GPUs. You know, it's so often when I talk to clients and users, you know, and you want to engage in these discussions engage in discussions on, you know, breadth and ease and number of people that are using accelerated computing. We got to make it easier to use. You know, one of the biggest hammers right now that I think is easing programmability is the coherency between GPUs, but more importantly, between the CPU and the GPU. I think again, you know, as you start pulling CPUs and GPUs closer together, even looking at APUs, it even gets easier. You never have to copy data. It's all shared memory between this, you know, kernel launch latency. Those things, you know, really improve kernel launch latency, make it very easy to run. Once you get the kernel launch latencies way down, when you start pulling the CPU and the GPU closer together, it makes it much easier just to say, hey, I'm gonna run wherever we want to run. And then, you know, I think, you know, we'll even look at, you know, looking at the future, I think we could even start looking at even attacking the architecture to improve ease of programming. And I think that'll be an important innovation as well. So I think we're doing things already, you know, making memory and the kernel launch latencies much faster to ease the programming. And then I think we'll start looking at architecture also.
And a couple of questions related to interconnect and memory. The first one, what about interconnect? Is there any strategic vision towards exascale?
Yeah, we don't, there's first of all, you know, interconnect, you know, is becoming, you know, much more a first-class participant in overall performance. And we need to, and we are, you know, got to drive those latencies down. We're seeing it more and more, even on the AI side. as these models are exploding, one of the things that we're definitely seeing a lot of is that the interconnect, the GPUs that are doing so much of the training are actually overpowering the interconnect. And what do I mean by that? We're not even able to keep the GPUs busy with even some of the fastest networks that we have available. So we gotta go ahead and start integrating that interconnect closer and closer to the accelerating devices as well. Not just leave it attached to the CPU. So I think that's very, very important. And then there's a lot of people out there that are driving so much innovation around and I think you've seen it. Driving the innovation around the traffic management, congestion management within the interconnect, and those are having first class, first tier impact on overall performance as well. And I think that's going to be an important piece also. So we're going to integrate that network closer to the GPU, I believe, get that latency to the network down, get that balance, so that we can keep all of those compute elements busy. And then, we of course have to keep doing things to improve those network implementations.
Related question. Can you comment on HBM use, HBM-based die logic used for acceleration? So
yeah, I saw that one. I don't have a ton to add that's really different, because I think much of that discussion of bringing that base die logic into into a more of a first class participant, I think all my comments about in memory computing very much apply, and I don't want to just repeat them all over again. I think it's the same point. Moving that everything about this efficiency is moving the computation more and more tightly integrated with the storage. I think that's where the future lies in efficiency and scale. And I think base die computation on HBM is very similar to the discussion of in memory computing.
Perhaps a question related to your previous comment on accelerators. How important are accelerators for exascale computing?
Oh, I hope I was transparent and clear enough. We're not going to get there without the accelerators, and I just a total opposite end of the spectrum. I think we're going to see more and more accelerators, more and more targeted to workloads. And I think that's where the winning is going to be, understanding the workloads really well and building computational elements to go and attack those various workloads. That's how you get to those large scales. And I'm me personally, I'm a firm believer that's the path.
Next question. How can we achieve exascale computing in embedded systems, for example, in highly automated driving, for example, for mixed critical systems?
Yeah, I'm gonna just read the question here just so I can understand it a little better, Diana. I think I see it right here, Diana. How to have exascale computing in embedded systems. Yeah, I think what that question is trying to get to, and we're seeing this, right? We're not putting exascale computers into the trunk of a car, but we are putting those same computational elements into the trunk of the car that are participating in exascale computing. I am seeing that. Many of our same designs that we're using to scale up to an exascale are also looking as strong candidates in embedded systems. And I think what that comes down to is there's such a strong linkage between an embedded system is so driven off of efficiency and performance as just like an exascale, that if you take a computational element out of an exascale system, it looks really, really efficient where you need it in these embedded and edge devices where efficiency is at such a premium. And we are seeing that. I'm seeing those trends. I'm seeing that interest. If you look at what you need to do autonomous driving, is very, very similar to what a node of an exascale computer is going to look like. I think that there is a lot of truth to that.
Our next question is on the use of emerging non-volatile memories. Is AMD considering using them in future systems?
Oh yeah, yeah. I think the non-volatile. I alluded to that in my last page, and I do firmly believe that again, all about efficiency. If you look at you start doing the breakdown of any large scale cluster. I haven't looked at it, very, very recently, but when I was looking at it, half the power, half the cost of the computer is wrapped up in the memory subsystem. So if you want to go and drive efficiency, and you want to go and scale the larger systems, get to an exascale and beyond, you've got to be going and attacking your storage elements. And and there's no tree that grows straight to heaven there. So me personally, my belief here is we're going to get to those non-volatile memories and get to those higher scales through tiering the memory, right? And I think you'll see that very much. We're not going to just take all the DRAM out and shove in non-volatile memories, but we're going to put some very, very, very fast DRAM close to our processing elements. Like we talked about the in-memory computing, maybe even move computational to those memory elements. And then we're going to put tiers of slower, lower power, more cost-effective memory further out. I think that trend is pretty clear that we're heading down that way. So I think that's a very important element moving forward.
In your presentation, you mentioned packaging. What is the motivation towards 3D packaging? Does it give any benefits with respect to power performance area?
Absolutely. I think there's a lot of motivation on power performance and area. Again, when you start using the third dimension, so much of the power of these chips is consumed, driving the computational elements, and passing the memory and the data around between the chiplets, right? We had to go to, as I showed in that evolution, we had to go to the chiplets and the smaller dies to hit sweet spots on cost performance, on die and yield, and be able to drive that efficiency. Great. Now you got more communication taking place. Horizontal communication, these packages, is expensive. It's very when I say expensive, I mean power consumptive, and it drives a lot of cost in the packaging. Start stacking them 3D, start putting, vias on, 10 micron and less pitch, going vertically up through the stacks. That's a big power reduction, and it's a bandwidth improvement, right? So we had to go to the smaller elements and to get to the right cost performance points. Now you got to move a lot of data, but you can get that computational density, and that's a lot of performance when you can move a lot of data vertically through those stacks. So yeah, there's the 3D, I think, is going to drive lots of things, and plus just give us the ability. I mentioned that just give us the ability to get more computational elements, get more stuff physically close together, and then insert the whole in-memory computing arguments again.
A couple more questions on programmability. What is your take on how to support HPC and AI, ML, and analytics workloads on the same platform?
Well, we're doing it now. I mean, playing to an audience of HPC people, all those AI people looked at our the HPC platform and said, "What a great way to do AI," and have started building the APIs and the frameworks on top of the HPC platforms to do that. So I mean, it's being done. I do think, and I mentioned it as I talked about our splitting off of the architectures between the visual architecture and the computational architecture. What is happening, right, that is very real is, AI is such an important workload. And while it's very, very similar to HPC, it's a little different. We're working in a much, much different spot on the precision of our data formats. I think it was important to, because we did it, I obviously thought it was important, to move something off of the die, because the biggest risk is that the GPU gets so burdened, supporting such a breadth of workloads that it becomes inefficient and we lose the cost performance advantages that it can offer. I think, the software stacks, I think we're doing a good job. The whole industry is doing a good job of building common software stacks to address the HPC workloads and the AI workloads. And I think it's important to keep it all on to the same platform. And we're seeing that, right? It's well documented and well shown that AI is going to do so much to advance HPC in our workloads, making them more efficient, making them so that we can get more out of our HPC. I think keeping those two workloads together onto the same platform is important.
Okay, with this, I know we have more questions, but unfortunately we have come.
Them all, Diana.
We are close to. We're at the end of our session, so I would like to thank again Brad for giving the keynote, and thank you all for attending, and thank you for all the great questions. With this, the session is concluded, and thanks again for participating.
Yeah, and add my thanks too. Thank you, Diana, for hosting such a great conference, and thanks everybody for coming.
Thank you, Brad.
Yeah.
Thank you, Brad. Thank Diana. I'm the chair of the session. I think we can disconnect now. And thank you, everybody, for participating. I'm Ellie Brad for this great talk and his participation to HiPEAC virtual edition. So bye-bye, everybody. Ciao.
Bye.
Thank you very much.
Thank you. Bye.
Bye.